Episode 14, Page Replacement Algorithms. Welcome back. In the previous lesson, we explored the magic of virtual memory, which allows the system to run more processes than the physical RAM can hold. This situation is called overallocation. It works smoothly until an inevitable problem occurs. A process requests a new page, causing a page fault. But all physical frames are already occupied. To load the new page, the operating system must do something difficult. Choose an existing page in memory to evict to disk, freeing a frame. The chosen page is called the victim page. The task of selecting the optimal victim page is exactly what page replacement algorithms are for. Their goal is to minimize future page faults. Part 1. Mechanism and Evaluation. Note 161 to 170. 1.1. Page Replacement Process. The page fault handling process now has an extra step. A page fault trap occurs and is sent to the OS. The OS locates the required page on disk. The OS checks for a free frame. Assume none is available. The OS runs a page replacement algorithm to choose a victim frame. The OS checks the modified bit dirty bit of the victim page. If the bit is 1 dirty, the page has been changed since it was loaded, so the OS must write it back to disk. If the bit is 0 clean, the page in RAM matches the disk copy, so no costly write is needed. The OS loads the new page from disk into the freed frame. The OS updates the page table and related tables. The OS restarts the process at the instruction that caused the fault. 1.2. Reference string and evaluation frames to evaluate algorithms. We use a reference string, a sequence of page numbers accessed in order. Example 701203. 04233032, with a fixed number of frames, say 3. We simulate and count page faults for each algorithm. Part 2. Classic algorithms. Note 171 to 182.1. First in first out, FIFO. Simplest algorithm. The OS maintains a queue of pages in memory. Rule. The first page loaded is the first to be replaced. Example with 3 frames and the reference string above. 7 gives fault 7. 0 gives fault 7 0. 1 gives fault 7 0 1. 2 gives fault replace 7 to 0. 1 0 gives hit, 3 gives fault replace 0 to 3 1, so on. Problem. FIFO may remove frequently used pages. Worse, it suffers Bilaty's anomaly. Sometimes adding more frames increases page faults. FIFO is rarely used in practice. 2.2. Optimal algorithm, opt or min, theoretical best. Rule. Replace the page that will not be used for the longest time in the future. Example. When replacement is needed, look ahead in the reference string and evict the page used farthest in the future. Problem. Not practical, as the OS cannot know future references. But OPT is valuable as a benchmark, giving the minimum possible faults. 2.3. Least recently used LRU. Practical and effective. Approximates OPT, based on locality principle. Recently used pages are likely to be used again soon. Rule. Replace the page that has not been used for the longest time in the past. Implementation challenges, costly to track perfect usage history. Method 1 counter. Each page entry has a timestamp. Every access updates it. On replacement, scan for the smallest timestamp, give slow method to stack. Maintain a stack of page numbers. Every access moves the page to the top. Bottom page is LRU. Stack operations are costly. 2.4. LRU approximation algorithms. Since true LRU is expensive, OS use approximations with hardware support. Reference bits. Reference bit. Mechanism. Each page table entry has a reference bit. Initially 0 on each access. Hardware sets it to 1. Second chance algorithm, clock algorithm. Works like a circular FIFO queue with reference bits. A pointer scans pages. If a page's reference bit is 1, reset it to 0 and skip it. If a page's reference bit is 0, evict it. It has not been used for at least 1 full cycle. This strikes a balance between performance and cost, and its variants are widely used in modern OSS. Conclusion: choosing a victim page is a trade-off. FIFO is simple but weak. Opt is ideal but impossible. LRU is effective but costly. Approximate LRU methods, such as second chance clock, with reference bit support, became the practical solution, delivering good performance without excessive hardware or software cost. With page replacement covered, we are close to completing the picture of virtual memory management. In the next lesson, we will discuss a dangerous phenomenon when page replacement is excessive: thrashing. See you then.